Welcome to the Petroleum Engineering Department at the University of North Dakota. Today we'll be walking you through our advanced labs. In our lab, safety comes first, and our students' safety is our main concern. For this, before coming in, you'll be asked to put on your personal protective equipment, follow the general lab safety signs, and each equipment-specific safety instructions. This is the core floating equipment. With this, we can perform several tests, from simple measurement of absolute and relative permeabilities to advanced enhanced oil recovery projects like water flood, chemical injection, polymer flood, and CO2 and different gas injections. This is our control station from which we can control all the valves and remote all the pressures. We have two syringe pumps, one on the bottom, one on the top, one on the bottom. And this is the heater in which we can mimic the reservoir temperature. Inside the heater, you can place your core sample in this cylinder, which we call core holder, and we use these two cylinders to inject whatever fluid we have. So this is a very powerful tool that can help reservoir engineers to characterize their reservoir and forecast many scenarios. Using the data acquisition system that can record the data that you have generated on every second, you can use those in your numerical model in order to calibrate it, and then you can upscale the results to a field scale.
Welcome to the drilling simulator DrillSim 5000. This is a field scale drilling simulator, sophisticated, that can allow us to do a variety of operations. From offshore to onshore, from vertical to deviated to horizontal wells, from top drive to rotary table drilling to downhole motor drilling. In this lab, we have different components. From our control panel, where we control our rotary or top drive, our draw works, our mud pumps and cement pumps, to our brake, and here we can see all the gauges that can allow us to track the parameters during the drilling operation. To the BOP, the blowout preventer, with different valves from annular to pipe rams to shear rams. We have also some digital displays. Here, for example, we see a subsea BOP for offshore cases. Also, we have other digital displays where we can track our data for data display, our auxiliary, our systems, our everything we can control from these digital displays. This other equipment is our well control panel. After a kick happens, we use this device or this piece of equipment in order to get that kick out of the well. This is our control station, where the engineer can operate all these equipments and manage the simulation. We can track the wellbore, geometry, the drilling string, property, the bottom hole assembly, and we can even use our joystick here to change the view in the rig. With all these equipments, we can simulate a real case drilling operation in a safe way. Students are allowed to do mistakes in the lab. However, engineers, they don't have the right to do mistakes in the field, because mistake during drilling can cost life. And this is the purpose of this lab, is to do experiment in the right way and teach students how to do it in an appropriate way. And in case they face a drilling problem, they know and get familiar how to solve this issue. This field scale equipment can allow us to do a variety of simulations. Students are allowed to do some mistakes, and they learn out of them. They learn how to deal with a kick, how to deal with a blowout. However, when you go to the field, a mistake can cause damage to equipment and can cause some fatalities. This is why it's very important to be trained enough how to operate these equipments. This is the purpose of this lab.
Hello, this is Autolab 1500. Autolab is a functional terrestrial device for measuring petrophysical and mechanical rock properties in in situ conditions. This system can which it used the 4 pressure intensifier to generate confining pressure, core pressure in upstream and downstream, and differential stresses. Also, it should be mentioned that the core pressure can go up to 20,000 psi. Second one is electronic control panel, which you can generate the pressure and control pressure here, or you can change the temperature and also observe different wave of velocity. The third one is autolab software, which you can collect and analyze your data and all experiment in a report sheet. Different role holder are available for different experiments. This one is used for permeability measurement. You can do permeability measurement either steady state or transient. With a steady state, you can measure permeability up to 500 millidarcy, but for ultra low permeability, you need CO2 holder, which you can measure on up to 5 nanodarcy. There is another core holder which is used for measuring velocity, ultrasonic velocity. Also, you can measure resistivity as a function of wide range of frequency, stress, and temperature. This complex equipment facilitates measuring both physical and geomechanical properties, and it's a great combination for both geomechanical and reservoir required data. Thank you.
So we also have the interfacial tension equipment. This is a powerful and simple tool that can measure both interfacial tension and wettability. They are very important parameters in fluid transport in porous media. The wettability and interfacial tension are measured using sisal or pendant drop method, in which the property is a function of the shape of the droplet of fluid inside another. So here we have our measuring chamber in which we load our both fluids. These two are our fluid accumulators. We store our two fluids, like for example oil and water. We use this pump to displace them inside the measuring chamber, and we have the camera and the light source. The camera helps us to catch the shape of the formed droplet, and then using the shape of the droplet we can measure both wettability or the interfacial.
Hello, welcome to the BVT lab. This is educational fluid level system. It's a compact PVT cell that designed for measuring small volume of PVT analysis, thermodynamic properties, and phase behavior of the black oil and gas condensate samples. The system is consist of 4 main parts, started with the control panel, and here we can switch on the system or the power and temperature, stirrer, and the light. The second part, which is the pump, and here we can generate up to 10,000 psi pressure using each one of the method, either constant flow rate or constant pressure. And we can filling the pump by using tap water to displace this piston to reach the desired pressure inside the BVT cell. And here the main component of our system, which is the head and BVT cell. The head composed of valves. This micro valve we can have the specific volume of the sample, and here these lines we can transfer our fluid samples from the oil reservoir or gas reservoir inside the BVT cell. And here we have 2 glass windows, and these we can visualize the interaction between oil and gas during the flash test. And we have light and camera to record this interaction. The BVT cell is consist itself with mixer mounted with piston, pressure transducer, and electrical heater to have homogeneous temperature system up to 350 degree Fahrenheit. And finally, we have here the data acquisition system. We use the specific software to calibrate our test. Then we select either constant mass expansion or constant mass depletion test to generate results related to our crude oil sample. Thank you.
Hello, my name is Ahmed Ismail. I'm one of the PhD students at the Petroleum Engineering program at University of North Dakota. I want to share with you one of our lab equipment that was built here indoors by our students at Petroleum Engineering and different disciplines. That's our drilling rig. It was built for the drill robotics competition and for other studies related to the research. Here we have our user interface, where the software is built by UND students, where you can acquire the different drilling parameters. Here we have the instantaneous values of torque on bit, bundle pressure, bundle flow rate, RPM, rate of penetration, and weight on bit. If you are doing directional drilling, then we have our real-time displacement or real-time coordinates displayed right here. On the other side here, we have a real-time display for the different parameters curve to observe the trends for the different curves and compare and see if you have any problem while drilling.
The multi-phase flow loop is used to simulate the multi-phase flow in the production engineering. The water is injected into the vertical tank from the water tank. The air is injected into this vertical pipe by the air compressor. Then the water and air will be mixed in these experimental pipes. With the increasing of the flow rates, the flow readings will change from the barrel flow to the slack flow, then to the churn flow, and finally to the annular flow. The data of pressure and flow rates will be recorded by the National Instrument LabVIEW software. Our water flow loop is used to detect the leakages and blockages during the transmission of the oil and gas. The fluid goes from the water pump, then to the flow loop, and goes back to the tank during the experiment. The pressure sensors are installed in the inlet and outlet of the pipeline. The water flow rate is recorded by the flow meters. The data of flow rates and pressures will be transferred to the computer by the software of LabVIEW. Then we can build a mathematical model which is based on the data we collected to detect the leakages and blockages in the pipeline.
Other than those labs, we have the virtual reality lab, where students are trained in 3D environments. Through simulations, they can virtually interact with real field equipment and experience different field operations. Now, let's go inside and check it out. Here we have 4 stations. Each station contains a powerful computer, VR goggle, headsets, and controllers. The capacity of this lab is limitless. We can upload several scenarios where we can train our students on different petroleum engineering operations. Now, let's see the student getting immersed in 3D environment to learn the steps of hydraulic fracturing operations.